everybody. You guys are listening to SG2 on Space. This is your host, Shengun, episode number 29. All right, so after a journey of quite a bit of me talking about the news and such, got somebody who is interviewing today. His name is Gerardo Viza. I've actually known him since our mutual Georgia Tech days, and apparently he continued the route of wonderful physics. And so he has a Bachelor of Science in Mathematics and Physics from Georgia Institute of Technology, and a Master's as well as a PhD in Physics from University of Rochester, particularly with a research focus on quantum optics. And then now he's a PTD module and integration device yield engineer at a company which nobody has heard of, Intel. I'm kidding. All right, Intel Corporation. Basically, working on lithography, which I'm not exactly sure what that is, but I'm sure he can talk more about that. Okay, so in any case, he is fluent in English and Spanish and a bunch of computer languages, which I am not going to go into. And yeah, and there's a bunch of papers he's written, so cool. All right, Gerardo, can you hear me?
Yeah, hi Chen. Thank you for having me.
Yeah, definitely. I've been trying to get you on the show for a while, but I'm glad this is working
Yeah,
out. So
thank you.
just let's start from the beginning here. This show is meant to be educational and interesting for the wide public. Um, so from the beginning, what okay, so tell me what are you I guess what are you currently working on if you're gonna put it in very simple terms?
Oh, sure. So a lot of the corporate world is, as well as some national labs, it's clouded in secrecy. So I can't really say specifically what I'm working on. But the just general idea is, so in Oregon, Intel does their R&D, their development of the future technologies. So right now, I think we're selling to 10 nanometers or 14 nanometer and 14 nanometer nodes. Um, so they have people not only doing those chips, but they have people working on like the 7 and beyond nodes right now. So I'm in that area trying to work on technology that hasn't come out yet.
So
So,
Gerardo,
and yes,
sorry, to clarify, you're working on chips.
yes, we manufacture. So Intel focuses on making server chips, and well, chips in general, CPU chips
Okay.
that are just a bunch of transistors
and
on
and
silicon
you're
wafers.
basically I guess one of the things they want to do is making smaller chips.
That's right. So the idea is to make things smaller, and by doing that, they'll make it more efficient and faster. Well, that's the idea and goal.
Okay, I'm sorry I have to take it from a high level perspective here before you go on, but all right, so with
Sure.
that clarification, so the fact that you said they're working on or you're helping to go to the 6 to 7 nanometer scale, is that what you said?
Well, that's just the name of the node. It's more
Ah.
of a marketing thing. Uh, so if you look at AMD's and Intel or TSMC, Samsung, what they're working on, they say, oh, we're working on this node of technology. But within that node, there's many steps. So right now, what you see on the market, I don't know what you call it, the eighth generation now, or ninth generation. I'm not sure what they're selling right now. That's one of the products that is made in Oregon. But
Mm-hmm.
the future technologies that haven't come out yet, like two generations or beyond, they they are tested and people work on them. And I'm one of those guys in there. that mix.
You're
Does that make sense?
basically designing the future.
That's right. Yeah. So, yeah, yeah.
Okay. So I'm sorry to go on a break this quickly, but it seems like
Oh,
that's
that's
what we have
fine.
to do. When we come back, I definitely want to talk about some of the past research you've done, and
Sure.
because I understand yeah, the fundamental research you can talk about, and clearly your thesis and papers are out there, so we can go
Hmm.
into some of the work you did at University of Rochester,
Yeah.
if that
Let's
works.
talk about that.
And yeah, okay. All right, cool. Let's take a short break.
Great.
Put your money where your community is. Get in the action at weareA1.com.
Okay, and we are back in the studio here of SG2 on Space, episode number 29. I was in a little rush, so I actually need to say one of those typical words first. Thank you for listening. If you're listening, you must be on www.facebook.com/The Shen Show, spelled TheShenshow. And of course, you can go to weareA1 .com to listen into the show and a bunch of others, kindly supported by Action One Media Group here on the Action One Media Group platform. And of course, their YouTube channel, you can look up Action One Media or SG2 in Space, also has this episode playing right now, as well as all the past episodes. And we'll have all the future episodes as well. So, a number of different ways you can do it. And of course, follow them on Facebook.com/Action One Media. All right. Good. Okay. With that spiel aside, I will have to say today we've been interviewing Gerardo Viza, who has a physics background and is currently working for Intel as a PTD module integration device yield engineer. Now, he briefly talked about how Intel is obviously trying to, to make computer chips, trying to miniaturize it, and he's part of the leading research group on the processes R&D development to get more powerful and smaller chips. For can't really talk too much about that, so let's jump back and talk about some of the research he's done. So Gerardo, you're on, right?
Yeah. Yeah, I'm
Okay,
here.
great.
Thank you.
So I see the giant word quantum optics. And,
Yeah.
for most of us, when we see the word quantum, okay, I'm not talking about myself, but a lot of folks, who may not have a physics background, see the word quantum, okay, that already intimidates them. And then the word optics, and then how those two. So maybe you can explain what quantum optics actually is before you go and talk about some of the things you've done.
Okay. Sure, sure. So yeah, these are very loaded terms, and in the context that you use them, they have maybe the definition can change slightly. How I'm using them is basically the study of how light interacts with matter, and in this case, light could be quantum, or the matter could be quantum, but at least one of them has to be quantum, or then what's the quantum about it, right? So basically, my grad school work was uh, working with lasers and atoms and studying behaviors um, of how these guys interact. Uh, Towards the end, mainly was just how light interacts with inanimate objects, like solid objects. But I did do some work with uh, rubidium atoms and cesium.
Okay, so you said quantum optics. Yes, it is a loaded term, and you're saying you're not actually using quantum mechanics?
No, so
The term,
let's see
and you're
how I say it. It's a loaded term. So light. When someone says light, what can make light quantum? Well, if you go to the single photon level, um, is actually if you look at it as from a coherent state. So if the light comes out of a laser and it's sort of every photon is very similar to the one right behind it and one right before it. That's sort of what you call coherent. Um, that's classical light, but you can do uh, some phase matching uh, conditions with some interaction in there, so that the light can become a little more exotic, give
mm-hmm.
it more correlation beyond classical limitations. So that makes it quantum. So if you have a quantum source, like let's say, or quantum material, like let's say a quantum dot,
mm-hmm.
you can shoot a laser at it and get a quantum source out of it, like a single photon being emitted because of the artificial atom that you're using. So you can shoot it with a classical light, and the quantum source will just the quantum dot will emit a quantum source of light.
So let's
Um,
stop right here for a second. You
sure.
mentioned a few terms which I'm not too familiar with.
Okay.
You said quantum dot, sorry,
Dot.
dot a few times, and somehow that's a quantum source. So what is a quantum dot?
So a quantum dot is an artificial atom where people fabricate them, uh, and it's like a small sphere, tiny sphere, where there's a ground state and a one excited state. So when you send a photon at the right frequency,
Mm-hmm.
and that quantum dot um, will absorb that photon, and the electron in there will be excited to the first excited level. There will be no room for any more photons. So when that electron will go back to its ground state, it will emit a photon, and that photon emitted by this single energy level artificial atom will have quantum mechanical properties. So it'll be a more exotic source of light than just a coherent source coming out of a laser.
Okay, I see. That's kind of interesting. All right, so got it. So from a high level, you worked with lasers.
Yeah, so yeah, right. So the majority of my life in grad school, been making lasers and playing with lasers, trying to understand how I can use them to interact with matter
Mm-hmm.
or to make measurements with them in a smart way or more of like a quantum way.
What?
Um,
Okay. Hey, what was your particular thesis? Can you talk a little bit about that and
oh,
why
sure.
it's important?
Yeah, yeah. So most of my grad school work with the successful papers have been on precision measurements. So in our regular world, we are bound with our classical source of light by the standard quantum limit. And this is engineering terms they call the shot noise limit. So
Mm-hmm.
it basically is that you cannot be more precise than what this bound predicts, giving all the parameters that you have in your experiment. So um, this limit is quite hard to get because it's clouded by a lot of noise. It could be technical noise, it could be systematic noise and electrical noise,
Mm-hmm.
uh, all sorts of stuff. And this is sort of what Intel and other companies struggle with. When you want to make something really small, you want to make sure it's very precise. I mean, consistent throughout the whole wafer.
Mm-hmm.
Um, so it's a big deal and very expensive to be very precise, especially at these atomic scales. So, yeah, so it's really technically hard to do to make these measurements. But if you look at it from a quantum perspective,
Mm-hmm.
um, the way of making a measurement is sort of a little different. And what I've focused on is called a weak measurement using weak value amplification to increase sort of the resolution of classical detectors,
Mm-hmm.
or increase the precision, the capability of detecting tiny signals, and and this will lead is making the tabletop optics experiments, or making them more precise. Or before, uh, one would not imagine being able to measure a mirror moving
Mm-hmm.
in the hundreds of femtometers per second regime, um, because of the noise. But one of the papers I published
Mm-hmm.
shows that I measured a mirror moving, I think, 400 femtometers per second. So in like less than 2 minutes, it will traverse um, like an atom, I think, one of the largest atom, average size atom.
Mm-hmm.
So that's pretty precise how you can um, measure precisely a mirror that's, I don't know, 2 inches in size, move. Yeah, so that's what I did. Studied lasers and how we can enhance the resolution, or the precision of classical detectors.
So let me understand this. You're in this experiment, you're moving a mirror.
That's right.
So a physical mirror, and this mirror. Let's see. Uh, so you were measuring how fast this mirror is moving.
That's right. Yes, that's
Okay.
right. Yes, yes,
And
yes.
I see. And you discovered that the velocity of that was 400 femtometers per second, which
That's right.
can translate into, you just said, take like about 2 minutes to go the distance of
The diameter
right.
of an atom. I can look it up. No, it's been so long since
Right.
I announced the
Okay,
first papers.
that's fine. So
Yeah,
and this what did this and this you used a quantum um what you just called a weak, what is it, weak measurement technique.
it's
And mm,
a weak, yeah, it's a weak measurement. I'm using weak value amplification to amplify this signal um, beyond what I guess classically you could
okay,
imagine and
so
observable to
right.
have.
So if you did this classically, basically without quantum mechanical effects incorporated in there, you will not be able to measure to that level of how slowly this thing is moving. Is that correct?
No.
Oh,
So
well,
the
all right.
experiment the experiment the experiment is all classical. But the formalism, so we write it in quantum, the Dirac notation, and then you can get your result. But you can also do it just with simple matrix, optics matrix. But the what you're doing is the quantum interpretation of it is quite fascinating. Where in quantum, if you frame things from a quantum perspective,
Mm-hmm.
the standard way of thinking, or as Griffiths would introduce it to us, that you have a wave function, and to extract any information from this wave function, you'd have to collapse it, destroy the resource. And it sort of goes along with the story of like Schrodinger's cat
Right.
in the box. You have to kill the cat, or maybe save the cat out of the box, right? Um, because a cat can be in a superposition of, you don't know if the cat's going to be alive or dead, but it could be in a superposition
Right.
of both
Right.
states, right? So, using that frame of thinking,
Mm-hmm.
that's only but maybe narrow is not the right way, not the right word to describe it, but it's one perspective of looking at quantum. But if you look at it from a more generalized perspective,
Mm-hmm.
what like what I'm going to tell you is, instead of opening the box, why not uh, entangle or couple this of observing the box with another system
Mm-hmm.
so that you can take small peeks into the box
Hmm.
and not have to kill the cat, but still extract the information: is the cat alive or dead, or both, or what percentage is alive and what percentage is dead. So you can. So that's what I focused on, where I looked at this problem
Mm-hmm.
from Schrodinger's cat perspective, a quantum
Mm-hmm.
perspective,
Mm-hmm.
and instead of totally destroying the wave function, I I just took a tiny peek and I left most of the photons just go straight through. So in a way, I'm not the interaction that I'm doing on the mirror, yeah, on the mirror is
Mm-hmm.
very small. So the mirror is moving really small. So the mirror is interacting with the wave function really tiny amount,
Mm-hmm.
really small amount, um, so that when I measure it, I'm just getting I think I measured like 8 million photons with a single photon detector. But yeah, something about that, and to get that precision. So it's a very small amount of photons to recollect almost 100% of that information. So that part is quantum, but the whole experiment is classical. I did use single photon counters, but it's debatable if that's quantum or not.
Okay,
I
so
would
the
say it is.
the key
Yeah.
point is this experiment you did, you could have done it with the classical measurement, but you decided to
Yep.
use this technique.
Yeah. So I did everything with classical devices.
Right, right.
Nothing in a super cold. Um, uh, I didn't use any supercooling system, or everything was just right. You can do it in your garage with the proper
Right.
experiment with devices.
Okay, understood. I noticed you had a number of other papers on this.
Sure.
So were they all related to using this weak value technique, or
Uh, yes, I think the majority of them are, if I remember correctly. Yeah, those are were the most fruitful. The ones with they got the biggest attention.
okay, I see. Huh, that's really interesting. You also mentioned a little bit about your rubidium thing, the
Yeah,
something to do with
right. I did.
rubidium. What is that about?
Yeah, I collaborated a little bit with another group where we studied the effects of fast light, slow light.
Mm-hmm.
Um,
What first of all, what is fast light? What is slow light?
yeah, yeah. So um, what I mean about fast light, slow light is when you send a pulse, or I mean the way you can
Mm-hmm.
send pulses. Um, there are two ways. There's if you look, if you can send a wave, right, and the wave we can call it envelope. But within that wave, you can have a different frequency of modulation inside that wave that can carry information. Now, what I mean by fast light and slow light is that you slow down or speed up that light um, in a medium. So in the medium in this case is rubidium, and uh, when if you hit the rubidium at where the let's see, the index of refraction is not constant,
Mm-hmm.
so that's near one of the resonances.
Mm-hmm.
Um, you'll have these weird effects where the group velocity of the wave packet or the pulse that you're sending in will speed up or slow down. So that's basically it. And if so, what I did was I looked at we looked at electrically induced absorption,
Mm-hmm.
and we artificially created a absorption dip. And in the bottom or close to the bottom of that dip, where things get absorbed,
Mm-hmm.
the light actually would the group velocity would go faster than the speed, the group velocity before entering the rubidium. So in weird situations like this, you can get light to go faster than the speed of light. But that's just the group velocity.
You said group velocity.
That's right. Yes. which you can't use to send information, unfortunately.
Okay, I see. All right.
Yeah, yeah. So that's basically my rubidium experience. I also toyed around with a magnetic optical trap, um, but that was more complex, and I didn't get any papers published in that.
Sorry, what was that on?
Magnetic optical traps, or maybe you've heard of a Bose-Einstein condensate.
Yes, actually, I have. So, wow.
Yeah, yeah. So the magnetic optical trap is sort of like the first stage before you go into Bose-Einstein condensate. Like a mott
Mm-hmm.
will let you go down to about 10 to the minus 6 Kelvin on your atoms,
Ooh, that's cold.
and then the Bose-Einstein condensate you can push 10 to the minus 9
Mm-hmm.
or more at in the Kelvin region, close to 0 to Kelvin. But it's really hard to set up. The lasers were a mess. It was hard, and that was my first experiment. So no fruit came out of that, but I did make some lasers. That was fun.
That is pretty awesome. Messing
Yeah,
around with lasers. Wow. Okay, that's pretty cool. So, since we are a space-based show, to a
yeah.
degree, can you talk about how some of your research is applicable to, say, say maybe telescopes or optical instruments used in space?
Yeah, absolutely. So, I mean, you maybe you guys have or talked about maybe Lego
Yes.
or yeah, like I know there's some fruit now in this.
LIGO, by
I
the way,
mean,
for folks
detecting.
listening, is the Laser Interferometer Gravitational Wave Observatory, and it's a
That's right.
large-scale physics experiment that's used to detect cosmic gravitational waves. So,
That's right. Yeah. So now I believe there's fruit in this field now, like actual concrete data that this is a working idea. So um, uh, the numbers are fascinating to me. I mean, Japan has something similar. They're using entangled light, I think, or last time I checked, they were working on it
mm-hmm.
to enhance their precision or to reduce their noise so you can get better measurements because the gravitational forces or um, the gravity emitted by these things that you want to detect are so small um, that just using classical light or small interferometers is possible to detect. So I saw. I mean, there's a lot of projects that were canceled from
Mm-hmm.
Europe about doing a interferometer up in space. Very aggressive ideas, but yeah. So my thing would be trying to use some of the weak value amplification in well, it's not my idea. I mean, many people have
Mm-hmm. What
wanted
idea
to
is
do
it?
this. Yeah. I'm sorry.
So, you're sorry, I interrupted you. What is this idea?
No. So this is not my idea. I mean, in the field, people that have worked, like the professors that have worked on weak value amplification, um, they've always toyed and looked at how we can make LIGO or how can we make these huge interferometers more uh, give them a boost of resolution. Um, and people have been implementing this. I think when I was in grad school, I was reading how Japan was they were wanting to push entangled sources as their light source for their interferometers to detect gravitational waves. So the idea is just to implement
Mm-hmm.
these weak value amplification ideas into these massive interferometers that we have here on the Earth to detect gravity waves.
So, is the reason that we're using like LIGO and some of these other ones to detect gravitational waves is our conventional telescopes unable to do it? Is that why we're doing this?
No, no. So it looks like our conventional telescopes have been able to do it. That's great. It's a massive engineering feat, what all these countries have done. But when weak values are sort of like the new guy on the block. Interferometers are something ancient, right? People have known about interferometry for hundreds of years, but weak values has it just started in the late 60s and the 70s, and then it just started getting a little steam, and then it sort of died down, and then it sort of picked up. I don't know, 20 years ago, something like that. So it's a new guy in the block, and who's going to want to invest on a new idea of your setup when you have your setup already there, millions of dollars. I don't know, maybe more than millions of dollars invested already. So there's a lot of, I guess, politics maybe, or maybe one pencil out. I haven't looked at the numbers recently, especially with the newer gravitational detector systems. But I would say, I mean, it sounds like an interesting idea to do.
Hey, I was just curious. Have you heard of the Fermilab holometer in Illinois?
Fermilab? I have not.
The holometer. I was just reading about it. That they're planning to build it, and it's going to be the world's most sensitive laser interferometer, surpassing LIGO and as well as Geo 600, the one in Germany. So, and theoretically,
can you say the name of it?
Huh?
Can you say the name one more time?
Fermilab, holometer, HOLOMETER. So, theoretically, it's supposed to be able to detect holographic fluctuations in space-time. And that's supposedly a property of some quantum gravity things. I don't know too much about that, but that sounds pretty wild.
Yeah, that'd be pretty cool.
Yeah. So, well, gravitational waves, black holes generated by that, so on and so forth. What I just said, which I didn't even know what it was. Are there more? So for your work, the interferometer, is it primarily used to detect kind of exotic things like that, or could it be used for more mundane observations?
Good question. I think it should be used. It could be used to see anything mundane. There's different regimes that I guess weak value amplification or the weak measurements work in. The weak value amplification part only deals with a tiny interaction, so something that's small. It's a nice thing to use for, but if you have a large signal, there might not be any benefit in using weak value
that's what I'm thinking.
Yeah.
Right. Okay. Yeah. That makes sense. It's just good for very sensitive, tiny measurements. Right. Okay.
Yeah, or measurements clouded in a ton of noise. Not all types of noise, but certain noise.
Okay. Yeah. That's for sure. That makes sense. It looks like we will have to take a little break. When we come back, let's talk a little bit more, and then we can wrap things up.
Sounds great. Thank you.
Money where your community is. Get in the action. Action 1. Independent thinkers working together. Inspiring action in media. Get in the action. Inspire today. Join us by being a sponsor at weareA1.com.
Growing up as a black kid in New Jersey, all I ever wanted to do was be a pro athlete. All of my role models were black athletes. And every time I would stare out the window, look at the sky, and wonder what I'd be in the future, it always had to do with me catching some crazy football and scoring a touchdown. When it came to the point that I was told that I would not be able to play on an organized sports team for the rest of my life, it was something that I really didn't even know how to stomach in the moment. And I remember walking out of my cardiologist's office and just sitting in the hallway and breaking down for a few minutes just because it it was something that I just couldn't plan for and couldn't account for. And I realized that in that moment, my entire life was going to be changed. And all of those dreams and hopes and aspirations that I had were going to go out of the window.
Man, you still here? Go on and subscribe.
Get into action.
Yo, we back at it again, baby.
What?
Get into action.
3.
Get into action.
Tell me what is the deal, tell me what is the deal.
So I challenge you today to start strong.
Get into action.
Tell me what is the deal. Cause I'm calling for you.
Get into action.
Can you feel that? See, I'm calling for you. Can you feel that? See, I'm calling for you. Can you feel that? See, I'm calling for you. Say how you really feel.
All right, and we are back in the studio. This is SG2 on Space, episode number 29, with your host, Shinga. Here at the Action One Media Studio, and I'm sure you're listening to us on Facebook.com/LeeShinShow or YouTube, the SG2 on Space, if you can look that up. So, today we're wrapping up our interview with Gerardo Viza, who is a physicist, presently working at the Intel Corporation on developing their next generation chips. And we've been talking primarily about some of the work he's done in the past and how it could be used for very precise telescopes, such as the LIGO one that measures gravitational waves. All right, so with a few minutes left, let's talk about something less technical here. So, Gerardo, what got you into all this?
Oh, hey, sure. So, in undergrad, I just kind of liked physics, and I loved thinking about just the formalism, how symmetric things were, how predictable things could be, and I thought that was pretty cool. How you can predict how, if you toss a ball in the sky, where it's going to land. Yeah. So as I studied physics, I met cool people like you along the way. That also liked science, and in grad school, I finally said, well, I like how this looks in theory and paper, but I want to see it with my own eyes, like you read about the double slit experiment, but when you see it physically with your eyes, that was a confirmation for me. Like, okay, this is what I want to do. To not only be able to predict phenomena that is counterintuitive or it boggles your mind, right? But to try to build a intuition based on this quantum weirdness and solve problems. So that's how I got into physics and how I got into quantum optics or weak value measurements. Yeah, I'm sure you have a similar story how you got into aerospace engineering and NASA, or all the space stuff.
Yeah, I mean, like you, definitely, Gerardo, I see the beauty in it as well. I mean, that's one of the reasons why I really enjoyed physics, and maybe I would go back into that one day. But okay. What's next for you? Are you planning to do some more fundamental research or help the industry, I guess?
Yeah, sure. So, one thing I want to clarify. So I am one of many. There's I don't know, at least thousands of engineers working on the next generation chips. it's my third year at Intel, so I'm sort of in the lower tier
Actually,
guys helping out.
let me
Yeah,
you don't have to answer that question then. So
yeah.
we're talking about chips and all, what is there is this a just a continuation of how we say, what is it, Moore's law? Chips
Yeah.
double in power every X number of years, and cost drops like half as well, and it's been going on. Is this part of that process that what Intel has been doing for a while?
Yeah, Intel's goal, as far as I know, is to try to stay to Moore's law or exceed it uh, every 2 years, and that's the goal from the top all the way down. But we encounter a lot of problems, so that's why they have to hire a lot of people to try to solve these issues, especially now where things are getting so small. They're practically like right there with the atoms,
Yeah,
Things are getting really expensive, really small.
I heard at a certain scale level that would be impossible to do. Are we
Uh,
reaching close to that?
well, yeah. So what we consider impossible, right, is impossible until you can find ways around it. Um, so yeah, we're approaching an area regime where our classical devices are a standard way of doing lithography. It just doesn't cut it. So Intel is working on many different ways of just going around it with the next piece of technology.
Okay, I see.
Yeah,
All right.
yeah.
Okay. Um. So, all right, I'm not gonna ask you what your future is, since gosh, who knows? Depending on what you're doing in your research lab or whatever. But let me ask you this. So I see that do you your own journey into now stem from you thought physics and math were beautiful and interesting, and you wanted to see this in reality, so you decided to pursue it. So if you have any words of wisdom for younger people starting out, what would you say to them?
Oh, well, gosh,
I'm putting you on the spot here.
education is expensive now. So, but thankfully, engineering and math and science, grad school is free. So, I don't know. I mean, most people, I guess, are not particularly wealthy. So, um, if you go towards the math and sciences, I mean, it's hard stuff, but definitely more economical than, say, a liberal arts major or I don't know, music majors. I don't know. It depends on finances for me. I mean, that's my perspective. But if you have the luxury of doing what you like to do, I mean, whatever you want to do, then that's another thing. But I just see the numbers of how everything's so expensive. University of Rochester's undergraduate degree, I think they're charging for a year $75,000. Who has $7,500,000 to pay for 1 year, right? Who does? If you have, great, go study whatever you want. But if you don't, like most of us, right, then try to think about the sciences and something that is that can be cool if you rack your head really hard.
No, I understand. The finances is very important. You're basically saying doing all this, what you said, say what you've done. The hardest part is actually being able to go into a good school where you can afford it. The actually doing the math and physics, that's not a big of a concern from what I hear you saying.
That's right. Yeah, I've met some engineering people who have done their PhDs in 2 years. That's great. But unfortunately, science is a little harder maybe than engineering.
Right.
It took me like 8 years, I think, to the master's and PhD.
Hey,
so it depends. It's a cost-benefit thing you have to juggle or think about.
I understand. Well, that's very, very helpful for people who wants to go in a particular field. Yeah, just remember, guys, grad school, depending on what it is, they will pay for you. For undergrad, you should watch out.
That's right. Yeah.
So, but as long as you have the smarts, you can definitely study this area, which is proven here, right, Gerardo?
Yep.
So
absolutely.
All right. Well, definitely appreciate your time spent talking with me and, basically illuminating what you're doing in this fascinating area of quantum optics to, I would presume the rest of the world. So thank you again, Gerardo.
My pleasure. Thank you. Thank you, Chef.
All right. So with that, we're going to conclude episode number 29 of SG2 on Space. Thank you for listening to us on Facebook.com. Oh, yeah. Follow me. Facebook.com/The Shen Show. TheShenShow. Follow Action One Media at Facebook.com/Action One Media. And, of course, check out the website at wearea1.com, as well as the YouTube channels for Action One Media and myself, which I actually neglected to mention before, but myself is youtube.com/CAST725. So, thank you, everybody, and have a great night. And never, ever, ever forget, look up. I know we didn't talk about UFOs, but look up anyway, because you never know what you'll see.
Peace, brother Atum Ryan. You tuned in the Action One Network.